Hello everyone, today I want to introduce to you one of the strangest particle ever proposed in modern physics, the axion. Axion, born as a particle proposed to solve strong-CP problem. The axion has now become one of the leading dark matter candidates. In a way, axion behave like a cosmic detergent, using the axion anomaly to clean up the CP symmetry problem in strong interactions. What makes them even stranger is that they behave like an extreme introvert. They barely interact with the baryon gangs around them, yet somehow they are deeply connected to photons. Under the right condition, they can convert into photons, and light can convert back into axions. So now the question becomes, how can light become dark matter? Good afternoon, ladies and gentlemen. My name is Gita Rahimi, and now I will explain to you the introduction to axions, and specifically, I will talk about axion-photon interaction, Primakov effect, conversion in magnetic field, and also other couplings. In this presentation, I will mainly talk about why axion exists, and also I will explain the interaction of the axion between axion photon and also axion fermion. And after that, I will talk about the cosmological role or the astrophysical implications. And finally, we'll be close with the current search in axions and also the future approach. Before introducing axions directly, we first need to understand why dark matter is necessary in modern cosmology. So based on the modern cosmological model, which is lambda CDM, the universe is contained 25% by dark matter, which is it's pretty larger compared to the baryonic matter. And one of the strongest pieces of evidence comes from the cosmic microwave background, or CMB, because CMB is essentially a snapshot of the universe about 380,000 years ago, years after Big Bang, during recombination era. Observations show that baryonic matter at that time was remarkably smooth, with density fluctuation only at level of about 1 part in 100,000. However, the present universe contains galaxies, clusters, and large-scale cosmic structures. Gravity alone would not have allowed baryonic matter to grow from such tiny fluctuations into the structures that we observe today quickly enough. This suggests that there is another form of matter that must have already begun gravitational clustering before the recombination era. Because this matter does not interact strongly with radiation, it could collapse before recombination and seed the later formation of galaxies. This is one of the main motivations for cold dark matter in the lambda CDM model. Additional evidence for dark matter coming from many independent observations, including common cluster velocity dispersion of galaxy discrepancy calculated from Zwicky in 1933, and also the famous galactic rotation curve observation observed by Rubin and Ford in 1978. And there's also gravitational lensing and common cluster studies with the galaxy cluster merger. Now we move to the original motivation for axions. In QCD, the theory actually allows CP piloting topological term proportional to theta QCD here. This term were naturally of order 1. It will generate a neutron electric dipole moment much larger than what experiment observed. We see here that just predicts it around 10 to the minus of 16, but experiment show that the EM is in the order of minus 26, which implies that theta QCD must be so smaller than about to the 10 of the minus 10 here, the theta QCD here. This creates a severe fine-tuning problem. Nothing inside the standard model explains why this parameter should be so tiny. This puzzle is known as the strong CV problem. The Pettit-Quinn mechanism solved this problem dynamically. Instead of treating data as fixed parameter, we promote it into a dynamical field associated with new global chiral symmetry called U1 Pettit-Quinn symmetry. When this symmetry spontaneously breaks at some energy scale Fa, a new pseudo-Goldstone boson will appear, this is the massless pseudoscalar axion. This is the equation of the field. And also, we will have non-perturbative QCD effects that will generate a potential that dynamically drives the field toward the CP conserving minimum, which in other words, the theory naturally relaxes to the state where CP violation disappear. You see here that from the Lagrangian here, with it's equal to theta QCD, it becomes a dynamical field that will relaxes to the zero when the potential coming to the minimum. So now we will talk about how the axion get mass, because previously we see that axion is basically a pseudo Goldstone boson, which is Goldstone boson is massless, but we know that axion has mass. So how does the axion get its mass? There's actually two ways to find this, but first we will talk about the curvature potential. So the axion begins as a Goldstone boson associated with the spontaneous breaking of the Pettit-Quinn symmetry, which in the limit of Fa, the exact symmetry limit, Goldstone bosons are exactly massless because every point along circular volley here, we see the point here is energetically equivalent. However, QCD non-perturbative effects slightly break this symmetry. Physically, instanton effects generate a periodic potential here for the axion fields. The once perfectly flexible valley becomes slightly tilted like this, creating a preferred minima. The axion field then oscillates around this minimum, and these oscillations correspond to a particle with small but non-zero mass. Because the tilt generated by QCD is extremely weak compared to the large Fa of the large Pettit-Quinn scale, the resulting axion mass becomes very, very naturally tiny. And also there's another way to finding the mass of axion before we calculate the mass directly from the lambda QCD, but here we actually could also calculate the mass from the pion mass. The reason why the axion mass become related to pion mass is that both particles originate from similar QCD dynamics. The pion itself is a pseudo-Goldstone boson, arising from chiral symmetry breaking in QCD, while the axion obtains its mass through QCD instanton effect. So it's pretty similar. Both are coming from QCD. Both masses are therefore controlled by the same non-perturbative QCD scale. In practice, The axion mixes slightly with neutral masons, such as the neutral pion. This causes the axion mass to inherit the characteristic of QCD energy scale that also determines pion's physics. So here we see that the mass of the axion is related to the mass of U here, but here mass of U is also related with the mass of pions. So we basically can calculate mass of axion through the mass of pions. And therefore, the axion is not arbitrarily light. Its mass is ultimately tied to ordinary hadronic physics, but suppressed by the enormous Petit-Quinn scale. There's several action models that ever proposed. Original PQWW action model introduced two Higgs doublets and predicted relatively strong couplings to standard model particles. Because of this, the action would have been produced abundantly and easily detected in laboratory and also the astrophysical observations. But we didn't find that, so the model was quickly excluded. We were not using this anymore. Because of that, modern visible action models solve this problem by pushing the Petit-Quinn scale to extremely high energies, which suppress the couplings. In KSVZ model, new heavy quarks are introduced. These are exotic quarks carrying color charge under QCD, but they not belong to the ordinary standard model fermion generations. A new scalar singlet field is also added. Singlet means that this scalar does not carry standard model gauge charge, so it mainly communicates through the Petit-Quinn sector. The heavy quarks couple directly to the axion field at 3 levels. However, ordinary standard model fermions do not couple directly to the axion at 3 levels. Instead, couplings to photons in ordinary matter appears through quantum Nook effects involving the heavy quarks. Because of this structure, KSVZ axions often called as hadronic axions. This has important experimental consequences. Since couplings to the electron are highly suppressed, solar production is dominated by the Primakov process involving photons in electromagnetic fields. Helioscopes such as CAS and EAXO are therefore particularly relevant for KSVZ type axions. In contrast, the FSZ model couples the Petit-Quinn symmetry directly to two Higgs doublets are already connected to standard model fermions in 3 level. As a result, ordinary quarks and lepton can couple to axions already at 3 levels. This means the FSZ axions interact more strongly with electrons compared with the KSVZ. Processes such as electron Bremsstrahlung-Compton scattering and atomic transition become important in stars. Consequently, stellar cooling observation involving white dwarf and red giants provide strong constraint of the FSZ type axions. Axions can couple to several sectors in standard model. The most important couplings are the axion-gluon coupling here, and also the axion photon and axion fermion. This slide summarizes the 3 major interaction pathways. The gluon couplings is responsible for solving the strong CP problem that we already discussed before. And the photon coupling allows the conversion between photons and axions in electromagnetic fields. Finally, the fermion coupling produces effects such as spin interactions and so-called axion wind. Each pathway opens different experimental and astrophysical signature. Now we arrive at the central interaction for this presentation, which is axion-photon coupling. The interaction term involves the axion field and the electromagnetic tensor. Physically, this coupling means that axions and photons can mix in the presence of electromagnetic field. The coupling strength is inversely proportional to Bete-Quinn scale, which means that realistic axioms interact extremely weakly. We say that if we derive the further tensor here that basically contains the electric and magnetic field, we see that the axion could interact with photons through the um, the existence of the magnetic transverse magnetic field, and it also should be external anyway. This interaction can also rewrite them into a more intuitive form proportional to the dot product between electric and magnetic effect. Magnetic fields. This equation tells us that an external magnetic field can induce mixing between photons and axions. In practice, the magnetic field supplies the missing quantum number necessary for the conversion process. This is why strong superconducting magnets are essential in most axion experiments. When the axion-photon interaction is included, Maxwell's equations become modified here. So from the Lagrangian, we just added new term for the interaction between axion and photons, and then we will find the equation of the motion by applying the Euler-Lagrange equation, and we will find here the modified Maxwell equation with the added term. And from here, we can also see the cavity, the cavity, the cavity system, which is with some assumption here, we see that axion Compton wavelength is large compared to the cylinder dimension, and also then the axion de Broglie wavelength is also large, which will later find that spatial gradient of axion field will be negligible. And finally, from those three assumptions, we find that axion field is approximately homogeneous in space inside the cylinder. So based on this assumption, we use this, we could simplify the equation, and then by deriving it, we will have the axion field oscillate coherently in time. There's a typo right there. Yeah. So in the presence of strong static magnetic field, this oscillating axion field can induce real observable photons inside a resonant cavity. This is the physical basis of holoscope experiments searching for axion dark matter. So when the axion here travel through the cavity in the presence of the transverse magnetic field, we see that with the Maxwell equation acts as a source, the axion photon coupling will later can induce real EM field or the electromagnetic fields inside the cavity. Yeah. And these fields are what experiments search for. One of the most important astrophysical production mechanism is the Primakov effect. Inside stellar plasmas, thermal photons pass near charged nuclei and interact with their electromagnetic field. Through the axion-photon coupling, some photons convert into axions. Since axions interact extremely weakly, they escape the star almost freely, carrying away energy. And also here, it shows the expected solar axion spectrum reaching the Earth. So in hadronic models or in KSVZ model, Primakov conversion inside the solar plasma is the dominant production mechanism. And here we see the graph that comparing the different production channels inside the sun. Here, the blue one is the Primakov effect, corresponds to photon conversion in electromagnetic fields of charged nuclei, and the Compton contribution coming from the electron-photon scattering process. FF here, wait, FF here is the free Bremsstrahlung interaction involving electron scattering of ions. And also we have FB, which is the free bound, added with the bond transition between discrete atomic. So both is basically between the electrons and bounded atomic states. Oops. And also the left spectrum here shows that solar axions inherit the thermal energy distribution of the solar core, peaking around X-ray energy, which is average in about 4.2 here, for 4.2 kV, with the flux rate of this equation. And the flux here refers to the number of atoms passing through a unit area per unit time and energy interval. In principle, Earth is continuously bombarded or immersed in this invisible solar axion beam. Modern helioscope experiments attempt to reverse the pre-Markov process by converting these axions back into detectable X-ray photons inside strong magnetic fields. The same interactions work in reverse. In stars, photon converts into axion through microscopic electromagnetic field generated by, generated by the interaction between the electromagnetic field that coming from the charged nuclei. But in the laboratories, we instead use the microscopic magnetic field generated by superconducting magnets. The magnetic field can be viewed as the source of the virtual photons, enabling axions convert back into detachable photons, because here we see that in order the axion could be converted into photon or the vice versa, the one axions need two photon, basically one real photon and one virtual photon. So here the magnetic field is basically served as a virtual photon for the axion. This inverse Markov effect forms the basis of helioscope experiments. Importantly, the conversion probability depends strongly on the magnetic field strength and interaction length, which is why experiments require extremely powerful magnet and long cavity. I forgot. Because of the probability scale here, it's related to BL. So yeah, we need strongest magnet and also longest possible distance. Finally, we're talking about the interaction between axion and fermion, which is the interaction is more into coupling into the spin itself through the derivative coupling here. If the galaxy is filled with an oscillating axion dark matter field, Earth effectively moves through an axion wind. To nuclear spins, this behaves like a tiny oscillating magnetic field. Experiments such as CASPER here attempt to detect these effects using nuclear magnetic resonance technique. Axions can interact with several sectors of the standard model. The most fundamental coupling is the axion gluon, this one, and also the coupling to the photons. But in addition, axions can also couple with fermions that we just discussed before, such as electrons, quarks, and nucleons. But more importantly, at low energies, interactions with quarks becomes effectively translated into couplings with nucleons due to the QCD confinement. As a result, axions may induce spin-dependent interactions, oscillating electric dipole moments, or pseudomagnetic effects. These different couplings determine which experimental strategies become most effective. Photon couplings motivate haloscopes and helioscopes, Electron couplings affect stellar cooling, while nucleon couplings motivate spin precision experiments such as CASPER. The cosmological role of axion emerged naturally once the flat space-time description is generalized into an expanding FLRW metric. Yeah, metric. In this background, scalar and vector field experience Hubble friction due to cosmic expansion. For scalar or pseudoscalar, here, the fields such as the axion, um, yeah, Axion, and from the field equation, acquiring a damping term that's proportional to the Hubble parameter, here, 3h. Early in the universe, when the expansion rate is extremely large, this damping dominates. Um, this damping dominates and effectively frees the axion field at some initial value. Later, as the universe expands and Hubble rate decrease below the axion mass, um, the field can finally roll down and begin coherent oscillation again. Um, and this oscillation behaves like cold dark matter because their average pressure becomes approximately zero. The same general mechanism also applied to vector fields such as hidden photon or dark photon. The underlying idea is identical. Hubble expansion initially freezes the field. In later coherent oscillation emerge. The difference lies mainly in the tensor curvature, tensor structure and polarization behavior of the field itself. One remarkable aspect of Axion dark matter is that origin may trace back to extremely early cosmological epoch, potentially even before the inflation. So when the Paget symmetry spontaneously break, the axion field emerge as the massless angular degree of freedom moving along the flat potential alley here. At this stage, QCD effects are still negligible, so the potential remain effectively small, flat. Later, the universe cools toward the QCD epoch, and instantaneous effects gradually generate the tilted periodic potential. However, during the early universe, the Hubble expansion rate is enormous. So the value of Hubble rate is above the the mass of axion. So it will create as the friction term in the axion field equation. And also this preventing the field from immediately rolling toward the minimum. The field becomes effectively frozen at some initial displacement angle. Only later, yeah, only later, when the Hubble rate drops below the axion mass, the friction weakens enough for the field to begin oscillating coherently around the minimum. From the perspective of quantum field theory, this coherent oscillation can be interpreted as condensate of extremely long momentum axion particles because the oscillation energy density redshift, like non-relativistic matter, the field naturally behaves as cold dark matter. This mechanism is fundamentally different from the thermorelic dark matter such as WIMP. Instead of being created through particle collisions, axion dark matter emerged from the dynamical relaxation of a primordial cosmic field. There's one of the important detection strategy, which is helioscope. It just track the sun with a strong superconducting magnet attempt to reconvert incoming solar axion into X-ray through the inverse Primakov effect. Additional systems such as buffer gases and X-ray optics improve sensitivity across different axion mass range. Today, many experiments and astrophysical observations have already excluded large region of the axion perimeter space. However, no confirmed detection exists yet. Importantly, the most theoretical interests in QCD Axion region remain only partially explored. Different experiments target different mass range and coupling strengths, meaning that the search is still very active. The next generation of Axion experiments aims to push sensitivity much further, using stronger magnet, quantum limit sensor, and broadband search techniques. Because the remaining parameter space is extremely difficult to probe, future experiments increasingly combine parameter physics, condensed matter physics, quantum sensing, and astrophysics. To summarize the overall journey, Axions began as a mathematical solution to the strong CP problem. The re-interactions made them natural dark matter candidate. Through the Birkhoff effects, stars can produce axions. And also cosmologically, axions can be produced from non-thermally through vacuum misalignment instead of collision. Despite not confirmed discovery yet, axions remain one of the leading dark matter candidates beyond WIMPs. So physicists are really obsessed with this axion. The axion began as a solution to theoretical inconsistency. Today, it connects quantum field theory, astrophysics, cosmology, and experimental physics. Perhaps one of the universe's biggest mysteries is hidden inside one of QCD's smaller parameters. That's all. Thank you. This is the references if you want to see. Yay, bye bye.